While playing around with shaders to try to create a way to visualize sound in Unity, I managed to create this neat effect here where we can see interference patterns between different waves. If you set the different frequencies, you get different interference patterns in the center. I'm going to walk you through how I made this and the math of how creating these waves and reading them actually works. So this is the formula for a spherical wave. It's a bit complicated, but I'm going to walk you through all the different parts of it. So what we want to do is we want to define this function in terms of the displacement. Displacement is the intensity of the wave at a specific point in space at a specific point in time. So what we need to do is we need to feed in the amplitude, which is the strength of the wave at the origin, the r, which is the distance from the wave origin, t, which is time, and then we have two more values for wavelength and frequency. However, you'll notice that wavelength and frequency aren't actually in this function. Instead, we have k and omega. Well, these values are actually related to wavelength and frequency, as they're both the angular versions. K is the angular wave number, and omega is the angular frequency. These terms are both related to wavelength and frequency respectively. So what we can do is we can find out what the definitions for those are and sub them into our equation. So if we separate these two out, you can see that we now have two new equations here. So the angular wave number is equal to 2 pi over lambda. So we can relate the angular wave number back to the wavelength. Frequency is 2 pi times the frequency. If we sub that into our equation, now we have it in terms of wavelength and frequency. But we can actually do a little bit more here because we can get wavelength in terms of frequency. So if instead of using the wavelength that we would feed in, we make it c over f, where c is the speed that the wave propagates in a medium. You've probably seen this before as defining the speed of light, and c does represent the speed of light in a vacuum, but it also represents the speed of any wave propagating through a medium. I'm going to use sound through air since it's a lot slower. So what we can do is we can sub this back into our equation for lambda, and now we have it in terms of frequency. We've cut out another variable. So now we only have 5 actual values we need to feed to this function. With these 5 values, for the amplitude, we're going to want to set this as the same for everything because we want to look at interference patterns between waves. So we're going to set that as the same all around, and we're just going to pick 1 for now. R is going to be the scalar distance from the UV coordinate of the pixel to the UV coordinate of the wave origin. T is just going to be time, and we're going to get this directly from the shader itself. Unity has it exposed. C we're going to set to 340. So the only value we actually need to feed in that will change is F, and this is going to be our wave frequency. So let's now break down this entire function and look at what the different parts do so we understand what we're building in the shader. This first term here, this is going to be the attenuation, which attenuation is the fall off of intensity over the distance from the source. All waves, the further away you get, the intensity of that wave drops by the square of the distance. So that's what our attenuation value is. And what I'm going to do is I'm going to get rid of the actual math in our equation and swap it with the name attenuation. Now for the second part within the cosine here, what I'm going to do is I'm going to pull this down, and this is going to be our time term. This time term tells us how fast the waves should propagate from the source. So in this case, since we have the speed set at 340, this is fixed, but what we're going to do is we're also going to multiply this by a scaled speed parameter. That way we can control the speed that the waves actually propagate outwards, so that way we don't have it either be horribly slow or blindingly fast. So that is our time term, and I'm going to sub that back into the equation. And then the next thing we need is our last term here. This is going to be our phase term, and this tells us what part of the cosine wave we're sampling. So as we shift this, it shifts the wave either left or right. So we're not actually going to use this in the shader itself. It's going to be the same for all of them, so they're all going to sample at the same point. But if you adjust that, it'll put the waves in or out of phase with each other. So now this is our final function. We have it defined as attenuation times the cosine of the time term minus the phase term. And this is what we're going to put into our shader. So this is our shader. What it's going to do is it's going to run a loop through all of our wave sources, and it's going to get the center of the wave, the amplitude, and the frequency, as well as the color. These are just defined in vector-4 arrays, and I pass them from C# to the GPU. Then we're going to calculate the distance from the center of the wave to the UV coordinate of the pixel. We want to get the angular frequency, which is what we defined as 2 pi times the frequency. We want to get the wavelength, which is the speed divided by the frequency, so 340 over frequency. Our angular wave number, which is 2 pi divided by the wavelength. Then our attenuation is equal to amplitude divided by the square of the distance. Time term is angular wave number times scaled speed times time.y, that's normal time. And then our phase term is going to be the angular frequency times the distance. Finally, what we're doing is we're adding to a color that I set as black originally, and we're going to add the respective wave color to it times our equation. So attenuation times the cosine of the time term minus the phase term. That is how we're going to add our colors, and this is how we get those interference patterns. I'm also just going to quickly show you what my C# script is doing. It's taking in a wave struct and it's converting it to vector-4 arrays and passing it to the shader. I have other videos on how to do this that'll be linked down below. Otherwise, this script is mostly just some garbage code that's very poorly written to figure things out, but we can ignore that. I will have this build available for you to download from my Google Drive. You can play with it, run it, but you can select where you want the waves to be from. If you want a fixed position, you can adjust the amplitude, so you have the intensity, and then you can adjust the individual frequencies of 3 different groups. By default, 1 is cyan, 1's magenta, and 1 is yellow. So you get cool rainbow effects when you add them together. So please feel free to play around with this as much as you want. Try to create cool effects. As you change the different frequencies, you'll get different interference patterns that pop up. So it's just a neat little thing to play around with. I built it in a single day, so don't expect it to be absolutely foolproof. But it kind of works, and it creates some neat patterns, depending on what you set the settings as. There is also another option, and that is that you can randomize the waves. So if instead of using the fixed positions here, we go up and we press randomize waves, now we have waves of randomized frequency in randomized positions, also randomized colors. So I can change the number of waves. I have the max set to 64, and the minimum is 1, but you can do that. You can also press use white and randomize it. So this is a white grayscale version, and I'd adjust the amplitude down a little bit, but it kind of looks like raindrops in water. And then if we use the move waves, this just updates the center of the wave every frame to be in a random direction. And then if it hits an edge, it reflects backwards. So they just bounce around, and I just thought this was a neat little thing to add. It only took me about 5 minutes, and I figured it might be fun for 2 or 3 minutes to play with. The last thing you can do with this is you can enter a path and save the image. If you don't enter a path, it'll by default go to the data folder of the build, so it'll be called wavevisualizer_data. There's also a couple other little things like this animate thing that controls whether or not the wave propagates, so you can have the waves moving without them propagating if you want to. But yeah, that's the entire tool. Let me know if you check it out. It's kind of cool if anyone gives it a shot. And thank you for watching.